Dear students, in this class I am going to start the second unit, in which you will be learning fast Fourier transform. In short, fast Fourier transform is written as FFT. The fast Fourier transform is a method or an algorithm for computing the discrete Fourier transform with reduced number of calculations. You know that if number of calculations are reduced, then the time required for calculation also reduces. Because of reduction in time required for calculation, the process of computation of discrete Fourier transform becomes faster. Hence, these algorithms are called as fast Fourier transform algorithms. In these algorithms, through these algorithms, the computational efficiency is achieved by divide and conquer approach. That means here DFT is not computed at once. Say for example, we have to compute 8-point DFT. If we go for FFT algorithm to compute 8-point DFT, 8-point DFT will not be computed directly. Instead, first 2-point DFT will be computed. Then, using 2-point DFTs, 4-point DFT will be computed. Using 4-point DFT, 8-point DFTs will be computed. That is why we say that in FFT, divide and conquer approach is used. So let us make a note on it. The fast Fourier transform or FFT is a method or algorithm for computing the discrete Fourier transform. That is DFT. In this method, computational efficiency is achieved by divide and conquer approach. Radix or FFT. In an endpoint sequence if n can be expressed as n equal to r raised to m, then the sequence can be decimated into r point sequences. For each r point sequence r point DFT can be computed. From the results of R point DFT, the R square point DFTs are computed. From the results of R square point DFT the R cube point DFT are computed. And so on until we get R to the power m point DFT. This FFT is called Radix or FFT. In Radix, RFFT algorithm used for computation of n point DFT there will be m stages of computation. Here in this chapter you will be learning Radix 2 FFT. For Radix 2 FFT, the value of n should be such that n equals 2 raised to m. That means it should be possible to express capital N as 2 to the power m, so that the n point sequence is decimated into 2-point sequences. And 2-point DFT for each decimated sequence is computed. From the results of two-point DFTs, the 4-point DFTs can be computed. From the result of 4-point DFTs, the 8-point DFT can be computed, and so on. Until we get n-point DFT. Before we go for development of FFT algorithms, we will compare the direct method of computing DFT with the FFT method of computing DFT on the basis of number of steps in computation. On the basis of number of calculations on the basis of number of calculations. Number of calculations in n-point DFT. Let x of k be n-point DFT of an L-point discrete time sequence x of n where n is greater than or equal to L. Now the n point DFT is a sequence consisting of n complex numbers. Each complex number of the sequence is calculated using the following equation. It's not a new equation. This equation we have already used. That is x of k equal to summation n equal to 0 to capital N minus 1 x of n into e raised to minus j 2 pi k small n upon capital N for k equal to 0, 1, 2, dash dash up to n minus 1. I hope you remember the x of k definition. If we expand this, we get x of 0 into e raised to 0 plus x of 1 into e raised to minus j 2 pi k by capital N plus x of 2 into e raised to minus j 4 pi k upon capital N plus x of 3 into e raised to minus j 6 pi k upon capital N plus and so on up to x of n minus 1, because here summation is from n equal to 0 to capital N minus 1. So the last value of n here will be equal to n minus 1 into e raised to minus j 2 into the bracket n minus 1 pi k upon capital N. Here each of these products are the complex multiplications, because e raised to minus j2 pi kn upon capital N is a complex number. And if we count the number of plus signs here, they will be equal to n minus 1 in number, because we are adding n complex products. From the above equation, we can say that the number of calculations to calculate x of k for one value of k are n number of complex multiplications and n minus 1 number of complex additions. The x of k is a sequence consisting of n complex numbers. Therefore, the number of calculations to calculate all the n complex numbers of the x of k are n into n equal to n square number of complex multiplications. And n into n minus 1 number of complex additions. Next we'll see number of calculations in Radix to FFT. In Radix to FFT, we know that n can be expressed as 2 raised to m. And so there will be m stages of computation where m is equal to log n to the base 2. With each stage having n by 2 butterflies. What is butterfly we will see later. The number of calculations in one butterfly are now here is a butterfly diagram shown. In this butterfly diagram you can see the dots here. These are points of summations. That means the numbers incoming to these dots, the numbers incoming to these dots must be added. And also you can see here arrow marks and some numbers beside these arrow marks. These numbers shown beside the arrow marks must be multiplied with the number that passes through the line. That is, if through this line A is passing, then that A must be multiplied with 1. So here the product will be A. A into 1 is A. Now that A has appeared here. Here is arrow mark shown, but 1 is not shown. That means 1 exists there. Or the signal simply passes here through the line. And at this point here, one more line is connected and that goes downward. Beside that also 1 is written, so A is to be multiplied with 1. So we get here A through this line, and here is Wnk. Here is Wn to the power k. That means B is to be multiplied with Wn to the power k. From this point, B into Wnk into 1 goes to the point of summation here. At this point, A and B into Wn to the power k are added. That we have written as capital E. And here, A into 1 is A, Wn to the power k into minus 1. It will become minus Wn to the power k. So, at this point, A and minus Wn to the power k are added. And that summation is called as B. So, if we look at this butterfly diagram, we come to know that there is one complex multiplication and two number of complex additions. So you can write here now one number of complex multiplication and two number of complex additions. There are n by 2 butterflies in each stage. Therefore, number of complex multiplications in one stage are number of butterflies in one stage into number of multiplications per butterfly, that is equal to n by 2. Similarly, we will write for number of complex additions in one stage. Number of complex additions in one stage are number of butterflies per stage, that is n by 2, into number of additions per butterfly, that is 2. On simplification, we get equal to n. The n-point DFT involves m stages of computations. Therefore, the number of calculations for m stages are m into n by 2 equal to log n to the base 2, because m is log n to the base 2. We have written it in previous pages into n by 2, that is equal to n by 2 into log n to the base 2 complex multiplications. And m into capital N equal to log n to the base 2 into capital N, that is equal to n into log n to the base 2 complex additions. Now we will write comparison table for computations in direct DFT and FFT. Number of points n. Direct computation. Here we will make two columns: complex additions and complex multiplications. Similarly, Radix 2 FFT, complex additions. Complex multiplications. We know that complex additions are n into n minus 1 in number. Complex multiplications are n square in number in direct computation. Whereas in Radix to FFT, complex additions are n log to the base 2 into n and n by 2 log n to the base 2. First we'll take n equal to 4. Four may be written as 2 square. In direct computation, complex addition number will be now 4 into 3 because n into n minus 1, that means 4 into 3, which equals 12. Complex multiplications in direct computation for 4-point DFT computation will be equal to 4 square, that is 16. Complex additions number is n into log n to the base 2 in Radix to FFT. That will be 4 into log this n, which is equal to 4, may be written as 2 square to the base 2. Log 2 square to the base 2 is 2. So 4 into 2, we get 8. Complex multiplication number is capital N by 2, that is 4 by 2, into log 4 to the base 2. It will be 4 by 2 into 2. It will be 4 by 2 into 2, that is equal to 4 only. In this way, you can write all the number of complex additions, multiplications in direct computation and Radix to FFT. For n equal to 8, 16, 32, 64 and 128. When you complete the table, you should have these values in your table. Yes, dear students, now I will stop your class and continue in next class with the development of algorithm for decimation in time radix to FFT. Thank you.